Okay, so welcome back again. This is the third lecture in the NanoNetworking course. This is the slide where we stopped last week, so we will continue from this point on. So let's discuss what's known about the mechanics of motility of the molecular motors moving over these microtubular network. So we're going to discuss what is precisely known about the motion of these motors and not known. We have already suggested how the motors move. Remember, we also had this video showing the animation about the movement. But let's go into some further detail. In the following slides, we will have some mathematics of this motion. However, you will probably have some difficulties in following the mathematics there because I will be skipping some of the details of this. You can go over the course textbook to better understand the mathematics beyond all this discussion. So the lecture is just giving the rough idea about this motion. So the stepping motion of the molecular motors over these rails is due to what we called last time to the conformational change in the molecule that attaches the molecular motor to this rail. Okay. Remember, we had the ATP attaching the molecular motor to the rail, the hydrolyzation of ATP to ADP and releasing the phosphate ion causes this conformational change, which means there's a change in the physical structure of the molecule, which changes the shape of the molecule. And due to this change in the conformation, the molecule makes a motion towards the other step over the rail, and this allows for the movement of the molecular motor. And this behavior is repeated over and over. This way the molecular motor is able to walk over the rail. So the rail is just serving like a ladder for the molecular motor, and it's like the molecular motor taking the steps over the ladder at the specific positions. At each step we have this ATP to ADP phosphorylation or ATP hydrolyzation event. ATP therefore plays a very important role in the living bodies inside the cell. This is actually providing the energy for all the operation. So it is the unit of currency of the intracellular energy transfer inside the cell. So in this role, ATP transports the chemical energy stored inside the chemical substance into a physical energy to transport the molecules or also organelles inside the cell. So ATP is typically produced as an energy source during the process of photosynthesis. So with photosynthesis, we get ATP and then make use of it. And also in cellular respiration, and it's consumed by several enzymes and several cellular processes where this molecular motor motion is one of them. So ATP is actually composed of the adenosine diphosphate, ADP, or the adenosine monophosphate, plus some phosphate ions. And it's used in the metabolism, converts it back to the building blocks. So there is always a change between ATP and ADP or AMP. And inside the body, actually, inside the cell, you're just reusing the same molecules over and over. The ATP structure is comprised of 3 phosphate groups, alpha, beta, and gamma. So in simple terms, the motor, remember, has 2 heads which are attached to these rails. And these heads are alternating with each other, attaching, and the back one releases and comes forward and attaches again. And this is how it moves forward. The binding sites are therefore analogous to steps on a ladder, as we explained. And when a head is released from the microtubule's binding site, which is that stepping position, due to the conformational change, the molecule makes a sudden swing in the forward direction and lands onto the next binding site. That's how you take the steps. The process is therefore repeated over and over, at each step actually consuming ATP, consuming energy. And this forward direction changes according to the molecular motor. As we said, kinesin and dynein work in reverse directions. So the head is attached to the microtubule, as we said, using ATP. And with the hydrolysis event, ATP loses one gamma phosphate group, and this leaves a space of approximately half nanometer between the head and the rail. And it is thought that this causes the rearrangement of the conserved structural elements near that ATP binding site. Finally, all this hydrolyzation loses the foot from its binding site to the from the attachment position. Therefore, with the conformational change, the head will swing in one direction and come to the next binding site and then attach to that binding site. And this will be our forward direction because this has caused a movement in one of the directions. The alpha helix is the common structure in most proteins. A right or left-handed coiled conformation exists, so it's resembling a spring in that sense. This causes a mechanical amplification in this movement, in swing operation. So the lever swings the head through an angle up to 70 degrees, not Celsius, I don't know where that C came from. And the lever swing is believed to be the ultimate cause for the working stroke. So the motors with longer necks take larger steps and they move faster. Remember, dynein was moving much faster. Okay. As we will see later, the neck, though we have always discussed what's going on with the heads, the neck also has an important feature. The shape of the neck actually is one of the factors that determines the direction. The head undergoes Brownian motion once it's released, but the motion is biased in some direction due to that shape of the neck and other criteria. And this bias is the result of two mechanical amplification procedures. One is the hydrolysis of ATP into ADP, and the tugging of the leading head. Now the head now experiences some strong random fluctuations, and collisions result in a directional Brownian motion. I will try to provide later another video where you see that the head is actually sometimes making back and forth cycles to find its correct direction. So this is actually what's happening. We also saw the video of this, so I won't go into the details of this, but here the two heads are attached. The neck and the load are not shown here. One of the legs, the lagging leg or head is released with the hydrolysis, and with the conformational change, the molecule or motor has a bias in the forward direction. But that leg, as I said, may try to find its correct position, and hopefully it will find the next binding site on the rail and attach there. And the same operation is now repeated, this time this lagging leg, which was previously the leading leg. So this was the case for the myosin 5, but for the others, the concept is similar. So to understand the thermodynamics of the molecular motor, and many other nanoscale operations, we should be able to calculate the information transport capacity and the energy required for the molecular motor's movement to operate. If we can understand the thermodynamics behind this operation, we can understand how much data we can transmit in this manner. So let's begin relating energy and force into this process, and to do that we'll be discussing the Gibbs free energy you probably remember from physics. So the energy change of a system, in other words, that in our case a molecule being stretched, as in the case of the molecular motor's movement, has two components: the heat exchanged and the work done. With the moment you get a work done, but as with all thermodynamic operations, there is also some heat exchange in this operation. It's not only kinematics. When the system is in quasi-static equilibrium, then the reversible exchanged heat and reversible work are as shown in this equation. So the change in energy is due to change in heat, the heat exchange, and the work being done. Okay? And this can be explained as temperature times the change in entropy. And the second term here, the work, is the work due to the pressure and volume, which is the negative of P times change in volume, plus some force being exerted for a distance of dx, which is integrated from the beginning of the moment to the end of the moment. Consider a single step, for example. You're at this position and you change in the x dimension. You take a forward step. So T here is a temperature. ds is a change in the thermodynamic entropy. And the others we already discussed. So Gibbs free energy is now the amount of energy available to do work. So it's therefore the total energy minus heat energy plus the energy available through temperature and volume. Okay? So the energy that turns into heat or increases the entropy of the system does not count towards useful work for our system. And it does not count towards the free energy. So the temperature and the pressure are typically controlled independent variables in such an experiment. So we can use a Gibbs free energy as defined in here. Gibbs free energy is the energy minus temperature times entropy, as we did before, plus pressure times volume, pressure volume forces. So now we can talk about delta G as minus entropy times change in temperature, volume times change in pressure, and as we said, force times the distance. So for the stretching of the molecule in this operation, for this conformational change, by an amount of delta x, the work required would be this force applied over dx, where you start at position x0 and you take a step of length delta x. If this operation is done slowly, which means we can assume there's no heat loss, the work is now reversible and equal to the free energy change in the system. So some positive work, if you have some positive work, that means, remember first of all, a thermodynamic system, a thermodynamic process is composed of the system we're looking at. In our case, that would be the molecular motor, and the environment. And there's some exchange of energy between the system and the environment, or the surroundings. So if we are talking about some positive work, that means the surrounding is doing work on the system. And the free energy of the molecule in that case is increased. If you measure the free energy change as a function of the temperature, then we can determine the change in entropy, which would be delta S due to the stretch of the molecule, and the change in enthalpy as delta H due to the stretch operation. And the enthalpy here relates to the change in the internal energy of a system, of our system, with the work done on the surrounding. So we can define enthalpy as H equal to Gibbs energy minus temperature times the entropy. So taking the previous expression, equation 14, we can determine 17, where delta S and delta H are defined as in here. So it's all up, and to come up with some results, what can we do? Let's consider two states, A and B. The system was in state A, then it's finally in state B. Each one occupies a local free energy minimum. Remember, this thermodynamic system tries to go to the minimum energy. So at position XA initially, and finally at position XB, separated by a distance of delta X, and in between with some mechanical movement we're trying to go from A to B. So A and B are representing the states of our motor in sequential locations, just beginning and end of a step over the track, or folded and unfolded states of the protein. It's initially folded and then released, it becomes unfolded. That's how the movement occurs. At zero force, which means no external forces here, the free energy difference between the states A and B can be shown as in here. So Gibbs energy, in case of no external forces in the system, would be delta G 0 plus Boltzmann constant times the temperature times the ln of the concentrations of state B and A. Now, the energy required by a force over some given distance would be then force times the distance. So this is, as we can see, increasing linearly if we're increasing the force. The energy increases linearly with the force and also with the distance. So the same equation, the previous equation, this time in the case of the existence of a force, F, would be almost the same thing with this added, actually subtracted. Okay? So when the system is at equilibrium, which means in that case delta G would be 0 due to the equilibrium, this equation is now simplified. So you end up with this part, putting 0 in here, taking this term to the other side, you will have delta G minus F times this delta X distance, which is a step length, equal to minus Boltzmann constant, temperature, and the ln of the concentrations. Now, here, this ratio is actually defining the rate of your reaction from A to B. Because this is due to a chemical reaction. On the left side, you had concentration of A, and on the right side, due to reaction, you end up with B. So, as you will remember, this ratio would be defining the forward direction equilibrium constant. So, what we see from here is the following. We note that by applying a force, the force F here, either in the direction of the moment of the motor or in the reverse direction. So either helping the motor to move forward or preventing the movement of the motor. The equilibrium state of the reaction changes. In other words, this external force exerted on the motor has some effect on the chemical reaction, on the direction of the chemical reaction, which changes the state or relative concentrations of A and B. In our particular case of a molecular motor system, the energy comes from the hydrolysis of ATP. So here we said we're talking about a reaction from A to B. Okay? Now in the specific case of the molecular motor movement, the reaction we're talking about is hydrolysis of ATP, which means ATP is converted to ADP and the phosphate ion. Okay? The outcomes are ADP and phosphate ion. So B, instead of B, now I can write the concentration of ADP times the concentration of the phosphate ion over the input to my chemical reaction, which was ATP. Okay? So whether this information is encoded as the concentration of the molecular motors themselves or a chemically encoded packet transported by a molecular motor, independent of that. Okay? So you can encode your information on the concentration of the molecular motors, or you may encode it as in the chemicals that are transported by the molecular motors from the center of the cell, for example, to the cell boundary, to the cell membrane. It is important to understand this relationship between the energy, efficiency, and the force of the motor. The molecular motors are typically exergenic systems rather than endogenic. So you remember exothermic and endothermic reactions. In the case of exothermic reactions, you're releasing energy, and just the inverse in the case of endogenic. So in exergenic processes, the energy is released from the system in the form of work, by producing work. If the pressure and the temperature are held constant, if you have no change in the pressure, there would be no reason for change in pressure inside your cell, for example, and the temperature would be the same, then the Gibbs free energy, which is the energy available in the system to do work, will be decreasing. In the case of an endogenic process, energy in that case would be observed by the system. And if we again consider constant pressure and temperature, the Gibbs energy in that case would be increasing. So a measure of the efficiency of the motor will be taking into account the reduction of free energy, Gibbs free energy, and the actual energy that performs the useful work. So we can define this efficiency, nu, as F delta over delta G, where F is the applied force of the motor, delta is the step size, the length of the step, what we previously talked about as delta X. So Gibbs energy now is the energy available to do work. So therefore, since the efficiency should not exceed 1, we say that F delta should be less than delta G. As the motor applies more force to move the load it's carrying, for example, pulling a large payload or maybe pushing an object like an organelle, the force F is going to increase, so the efficiency will also increase, but up to a point. Okay? Eventually, that force against which the motor is working will increase and increase, and the motor will finally come to a halt. It will come to a stalling position. Okay? It will reach a maximum, and beyond that it cannot pull or push anymore. Okay? Which is called the stall force, or F stall. The measured F stall values indicate efficiencies ranging in a very wide range from 15% up to 100%. So it could be anything in between, which is a very wide range. For motors with efficiencies less than 100%, it is hypothesized that the energy not going into useful work, now if it's 100%, that means you're not losing any energy. You're converting all of the energy to do work. That's perfect. And human-made motors, for example, cannot achieve this. Okay? If the efficiency is below 100%, that means you're not able to use all of your energy for producing useful work. Some of the energy is wasted. And that waste is due to either heat or it is used for generating forces that are not in the direction of the moment. They're perpendicular to the rail, which is determining your direction. Okay? So it was a force generated in an incorrect direction. Okay? So that force would not be producing any useful work. Another measure similar to efficiency would be the coupling constant, which is the probability that a motor takes a step per chemical reaction. After every chemical reaction, you take a full step. Okay? That would be the coupling constant. If the coupling constant is 1, then the motor is tightly coupled. Good. However, there is no direct relationship between the coupling constant and efficiency. You could have a tightly coupled system, but it may not be very efficient. Okay? A motor step can require several chemical cycles also, and its efficiency might be still very good because all of the energy that has been consumed has been converted to useful work. But in that case, the coupling constant would not be 1, for example. So there's no direct relationship between coupling constant and the efficiency. So going back to the stall force, we said the stall force is the maximum force the motor is capable to produce. Yet, you're not able to move. You increase the force more and more and more, but in the reverse direction, you also have some force, and you're not able to move at all, so the velocity is reduced to 0. That's the point where we can talk about the stalling force, the stall force. So making use of equation 19, now we can write the F stall value as, going back to 19 here. Where is it? Okay. Going back to 19 here. Just divide both sides with delta, which would be your delta x here. You end up with this formulation. Okay? Instead of delta x, just put delta and divide both sides with delta, and you will get this. Okay? So if you look at that, delta G0 there is again the Gibbs free energy with no applied force, and delta is the step size as we discussed. Remember that delta is xp minus xa. You were finally at xb position, but originally at xa. So with small step sizes, more force is required for the stall the motor. Whereas with larger step sizes, it would be the inverse. So if you look at this, small step sizes implies actually higher power to pull. This is very similar to the case in your cars. Okay, having small step sizes would be equivalent to working in lower gear. Okay, and the car pulls better if you're, for example, going uphill. Okay. In some cases, the process can also be reversed, which means, remember, when the motor is moving in the forward direction, it's consuming energy. Push the motor backwards, and it will start producing energy. It will convert ADP to ATP in that case, so it will be creating fuel. There are also such cases. So ATP synthesis via a reversible motor has been demonstrated, and the motor, when a large force is applied that reverses the operation, causes ATP to be created from ADP, sorry, not ATD, from ADP and phosphate ion. So one fascinating aspect of nanonetworking is the greater potential to leverage self-assembly compared to human scale networks. In human scale networks, you typically have signs of being scale-free rather than being uniform. So human-specific factors are now in effect, like the market dynamics and human interactions, whereas in the nanoscale networks, you don't have such effects. You only talk about physical properties. So they might be easier to manipulate and study. Another area of research would be the method used to deploy the topology of microtubule rails. So these rails should be deployed before you start running the molecular motors on these rails. There are two main focus areas in here. One is the self-assembly, and the other is the track deployment via lithographic methods. So in this reference 7, you can have information about that. Producing the microtubule trains, developing them with self-assembly is a natural process, and that's also explained in detail in reference 8. Self-assembly typically occurs naturally, in a natural manner, which is usually in thermally activated self-assembly process. So in another reference, you may, these are all available through the library, or if you want, I can provide them. In reference 9, self-assembly and some structural models are also explained for this purpose. So this naturally occurring biological methods use diffusion to bring the different parts of the microtubule. Remember, we said the microtubule is composed of alpha and beta tubulin, and this microtubule is, at one side you're creating the microtubule, but at another side, at the other side, these are dissolving. So alpha and beta tubulins will be dissolving into the cell, into cellular fluid environment, the cytoplasm. So you bring these together and again create parts of the microtubule. So it keeps on dissolving and also meanwhile growing. But this is a slow process, and it's really hard to control because these building stones, like the alpha beta tubulins, will just be floating in the cytoplasm. How do you bring them back to the correct place and then merge them together? This is pretty hard to control. But somehow it's occurring in the nature. The use of the molecular motors to propel and control self-assembly is proposed in yet another reference. This demonstrates the use of the molecular motors for self-assembly and how they may be speed up. One of the issues in self-assembled networks is the control over the process, studied in 11. These are all the things you can find in the literature on this topic, but going into the details of all these is beyond the scope of our course. So just a very brief summary of what is being done in the literature. So there have been suggestions also regarding the possibility of collision-based computing using microtubules. So the microtubule network typically forms within a soup of these smaller tubulant components, the alpha beta tubulins, like a soup inside the cytoplasm. And there appears to be a form of communication and organization that takes place at this fundamental level, which is typically mostly beyond our control at the moment. So the microtubules are very dynamic network structures, continuously decomposing, but meanwhile also forming newer threads. So this can be considered like the end of a thread milling. Do you know what thread milling is? Thread milling is actually making out ropes using a thread. So you're taking the alpha and beta tubulins together and producing this microtubule, and it goes forward. So this is just like constructing or forming thread out of components. Okay, and you bring up components together and you add it to the existing filament, and more and more and more, and actually what you're doing is you're pushing your filament in that direction by growing it from this side. Okay, so that's the thread milling act. So a section of the microtubule will be growing at one end. However, at the other end, it will keep on disassociating. But with the disassociation, you get the raw parts that are required at this side again to produce more and more filaments. Okay? So it has been suggested that there are turbulent trails, which are actually locations of high turbulent concentration, which are the components of this rail. And probably these are mostly due to microtubules that have just dissolved. Okay? Since you have high concentration of these tubulins, this is mostly because there was actually a microtubule there, but this has started dissolving. That's why that concentration is high at that point. And since there is so much raw parts in that region, the probability of constructing a new microtubule in this region is higher because you have all the parts necessary for this production. So while shrinking, a microtubule will thus be releasing a chemical trail of tubulin, because all those dissolved parts will be in that area, which quickly become active building blocks for new microtubules once they're associated with guanosine triphosphate, GTP once again. And these new microtubules will tend to grow towards the location of such turbulent trails, because wherever you have those turbulent trails, you have the necessary parts for this operation, for its production. So the rate of growth of the rail when this thread milling occurs is on the order of 1 to 10 micrometers per minute. Okay? Remember again, 10 micrometers is roughly like the diameter of a cell, just to give you an idea. So microtubule networks are very sensitive to external fields, such as gravity and magnetic fields. Changes in such fields have an impact on the formation of the microtubule network. So it might be possible to control the formation of microtubules with gravity and magnetic fields. The microtubule networks have a self-similar structure at several scales. So look at it closer and you will see the same structures repeating. That's what self-similarity is. And consumes chemical energy in the form of GTP to maintain the fight against entropy, which is the organized state of it. And the topology of the microtubule, or remember the actin filaments we previously discussed, for controlling the shape of a cell. Actin rail transport systems play an important role in molecular motor transport. So you can imagine molecular motors as trains running over these rails. Rails formed as we just discussed in the previous slides. There are two main types of biological rail topologies. One is uniaxial and the other one is centered. The centered one is centered around the centrosome, whereas the uniaxial systems are found typically in axons, which are like tube-like boundless filaments, whereas the centered ones, as I mentioned, is around the centrosomes, originating from the centrosome. Therefore, it is a star topology where the centrosome is at the heart of that star. Typically, the molecular motors moving over these rails consume some volume due to the motor itself and mostly due to the load it's carrying. That means if there's a molecular motor here, you cannot have another molecular motor here. It has to be somewhere else. Now, taking this volume consumed by the molecular motor and the others nearby, if there are many molecular motors close to each other, now we can talk about a traffic jam occurring over this rail. This is like many trains side by side on the rail. Then you would have a traffic jam there. Okay? Now that proves to be very important actually. In uniaxial systems, which are aligned tube-like bundles, the area where you have that traffic jam, the congestion, occurs, grows with motor density. Okay? More motors in some area, of course, you have more jam. And in the case of uniaxial systems, once that concentration increases, you will have more jam there, and this will spread throughout the whole system, throughout the whole rail. Okay? Whereas in the case of centered systems, the jams grow more slowly compared to uniaxial systems, and also that congestion dissipates as you go away from the center, and it dissipates also in a more complex manner. The impact of such traffic jams is important on the strength at which a molecular motor binds to that binding site. So it's also influenced by the volume of the cargo being carried by the motors. The larger the cargo, the more traffic jam you will have with the same number of molecular motors, because those larger volume cargo will take up more space. Remember, we talked about the Brownian motion for the movement of these molecular motors in several aspects. One was that once the head is detached from the rail, due to Brownian motion, it makes some random movements. But this was a biased Brownian motion. It was random but biased towards the forward direction due to the conformational change of that molecule there. But also, these molecular motors could be detached from the rails, for example. In that case, they will be floating inside the cytoplasm with some with the Brownian motion. So the motor will be subject to collision with the surrounding fluid molecules. Since we're talking about intracellular environment, we're talking about the molecules in the cytoplasm. But all those molecules will just be hitting at the molecular motor and mostly on the large cargo it's carrying. And these collisions may cause the molecular motor to get detached from the rail, in which case the molecular motor and its cargo will be floating in the cytoplasm. And during that floating operation, it's again subject to the Brownian motion. Experiments that track the motion of the motors detect a period of directed motion along the track, followed by periods of random motion, as the motor is loosened from its track and diffuses in that cytoplasmic fluid. So, in other words, what this bullet here says is the molecular motor, in the experiments they have observed that the molecular motor attaches to the rail, moves over this rail for some time, and then it gets detached due to these collisions. And hopefully somewhere else it will get attached to another rail and again keep moving in that given direction. If you have motor to motor or motor to filament interactions, which we do, there is a possibility of interesting self-organizing behaviors to occur, as will be discussed.
Is there any motor to motor interactions?
Yes.
How?
How? You will see in a few slides, but you can have motor couples. They are attached to each other.
Okay. And load carried by two motors, for example?
One motor moving over one filament, the other moving over another filament. This is like two trains attached to each other from the backs, and each one moving along the rails. Now what happens if the rails are getting further apart? In this case, one of the trains would get out of the rails, right? Well, it's just the inverse now, because now the train is attached to the rail so strongly that it will be pulling the rail. We'll come to that in a few slides. Okay? So one simple interaction is a spatial mutual exclusion. Motors cannot occupy the same space, as we said. A related effect is that high density of the motors on a part of a filament, with that, the ability of other motors to bind the filament is reduced. What does that mean? That means if you have a congested area, the force with which the motor attaches to the rail may be reduced because of the congestion. Because there are multiple motors attached to a given portion of the filament, and all these are attached, remember, with chemical bonds, and having so many of them side by side has a reducing effect for each other. So it's also known that the mutual hindrance slows down the movement of the motors in areas of high density. So congestion, in other words, has its effects. It's not as simple as saying, oh, there are so many of them there. First of all, can you have so many of them side by side? You have to look at the volumes that are consumed by each molecular motor and its large load, the vesicle it's carrying. Second, if you have so many of them side by side, the binding force will be reduced. And the third, it will also have an effect on the speed at which these motors are moving. The speed of the molecular motors, their processivity. Do you remember what processivity is? Once it attaches the rail, how long can it remain on the rail? That was the processivity. So that's a time spent bound at the molecule microtubule ends. These may have a strong influence on the patterns generated by the microtubules at this steady state. Interesting motor microtubule interaction is shown in experiments in which the motors are added to randomly oriented microtubules. At low motor concentrations, the microtubules remain randomly oriented. However, when the concentration of the motors is increased, kinesin forms microtubule vertices at intermediate concentration and esters at higher concentrations. Now, what does that mean? When the concentration of the motors is low, then microtubules appear to be randomly oriented. But if you put more and more microtubules on the rail, and if the molecular motors we're discussing are the kinesins, in that case, if the concentration of the molecular motors, if the concentration of the kinesin motors is at intermediate level, in that case you have vortices, microtubule vortices, which means the microtubule comes and there is some turning effect of the microtubule and continues, where you have an intermediate level of congestion. If it is even higher, in that case it is asters, which is a star-shaped structure topology. Okay? So a vertex is a spinning formation, whereas an aster is a star-shaped formation. And here the central mass we're discussing is the place where the congestion is. The speed and rate of rotation of the surrounding microtubules are greatest typically at the center and decrease progressively with distance from the center, especially when we're talking about the aster structure. The motors appear to accumulate in the center of the aster, and the motor complexes, that is what I briefly explained a few minutes ago. Now we're talking about motor complexes, like two of them together. They have been modeled as two identical motors which bind to one or two microtubules, or they diffuse freely in the surrounding fluid. These motor complexes, when they're bound to two microtubules, as they move, they exert a force on the microtubules. As I said, these are so strongly attached to the microtubules that they're pulling the microtubules towards each other, because the other side of the complex, motor complex, is holding the other microtubule. Okay? And as they move, actually, they form a V shape of these microtubules, because you have a motor complex pulling it here. Okay, so you're able to change also the shape of the microtubules, because these rails, remember, are actually floating in the cytoplasm. So a motor complex moving towards the end of two microtubules simultaneously typically will cause a V shape. Probably that could be the reason for the aster-shaped patterns that occur, because of the V is actually towards the center. V is forming the center. The microtubule network is typically comprised of, by the way, how about video time?
55 minutes.
55? Okay. Let me check which slide I'm in. Probably you'll cut the slide. Okay. Okay, let me continue, and then I will be leaving you early today. Rather than giving a break, let me finish the topic here, and then we'll stop. Okay. So the microtubule network is typically composed of chain segments that may or may not be straight. In general, the tube chain can range from a nearly straight line segment to a pretty curved chain. And the persistent length typically measures this curvature, where the persistence length is the length of that straight line segment. So a long persistence length indicates a chain that's very straight, while a low persistence length in that case means a highly curved spaghetti form microtubule. So the persistence length in that sense is the rate at which the tangents taken along each segment of the microtubule become decorrelated from each other. Okay? So if we now talk about a point on a segment S as RS, and letting US be the unit tangent vector over S. Now US is drs over ds. So the orientations of the unit tangent vectors now at different points for segment 0 and segment S is now quantified by the inner product of US and U0, which is as defined here, where we have the persistence length. Now, if you have longer persistence length, that means some long strip, or shorter tubes, okay, shorter rails, the microtubules will be, in that case, straighter. That defines a straight microtubule. Whereas, as the tubes get longer, or the persistence lengths get shorter, then the impact of decorrelation along the chain tangent becomes more significant, which means a curved structure of microtubules. So we can approximate the curved microtubules as many smaller random chains that are connected end-to-end, but with decorrelated alignments. So shorter persistence lengths will tend to decrease the percolation threshold, which is important in explaining the network conductance. So if we have an overlook to what we have discussed and also some more numeric values for you to use if you need to do any simulations in this field, microtubules have an outer diameter of 25 nanometers and lengths of several micrometers. So these are thin, long wires actually, curved or straight. They define morphology and provide the mechanical stiffness of the cell. Remember, that's why the cell grows like more like a spherical entity rather than being like a very thin sheet of organic material. The mechanical properties of microtubules have been studied extensively for over a decade. If you look at the literature, you can find a lot of information on that. And the consensus is that the microtubules can be characterized by a persistence length of approximately 48 micrometers. We said the microtubule tracks are composed of proteins, which we call as alpha tubulin and beta tubulin, where beta tubulin represents the plus end and alpha tubulin represents the minus end. Okay? And the microtubules are dynamic network structures that are continuously growing from the plus end. The minus end may be capped or it may lose its cap. And it may begin depolymerization or disassembling, whereas the kinesin motors move along the microtubules predominantly towards the microtubule plus end, and the dynein motors move towards the microtubule minus end. The myosin motors typically move along the actin filaments or pull the actin filaments, which tend to have a more randomized network structure in vivo systems. So long distance transport in cells is predominantly done by kinesin and dynein over these microtubular networks. So most kinesin motors move towards the microtubule plus end, but some of them move in the reverse direction. So kinesins, as we discussed earlier, are able to move in both directions, but different types of kinesins can do that. You don't have a single type of kinesin which can move both forward and backwards. So kinesin motors are able to carry out both plus and minus end transport in the cell, where dynein works typically in one direction. Maybe. So if you look at the paper in reference 16, it suggests that the directionality is caused by the neck or the stalk of the molecular motor. Remember, the stalk is the one that connects the heads to the load it's carrying, typically the vesicle or the organelle. Okay? So it is suggested that the stalk or the neck determines the direction of the molecular motor. The tilt of the stalk differs between different types of kinesin motors, which are moving in different directions, to the plus or the minus end. So the tilt of the stalk may impact the motor heads to attach to the microtubule binding site in the preferred orientation. That means, remember, one of the heads gets detached from the microtubule, and it is suggested that due to the shape of the stalk, for example, the detached head moves this way rather than the other way. Okay? Once the motors reach their polarized destination along the microtubule, due to the polarization there, when it reaches the end, it's not able to hold its load so strongly anymore. Therefore, the load is detached from the neck at the destination, which is what we want. And after that, also the microtubule gets detached from the rail so that it floats with Brownian motion and hopefully attaches in a good position to the microtubule once again and carries some other load. So they detach from the microtubule track, and with Brownian motion they just float in the surrounding fluid.
Sorry.
Yes?
The motor loaded within the fluid or on the microtubule? I couldn't get that.
Okay. Depends on what you mean by the load and where it is produced. Wherever that target is, actually, the neck, never the heads, but the neck will get attracted by the load that it can carry. Remember, all these are actually molecules. So it depends on the interaction between the molecules. So wherever the load is, depending on what you mean by the load, wherever the load is, the neck will get attracted by the load so that the load strongly attaches to the neck. And then with Brownian motion, they only get attached to a head, to the rail strongly, and then that ATP hydrolysis starts working, and depending on the type of molecular motor we're talking about, depending on the shape of the neck, it will find its correct direction, plus or minus end, and it will start walking in that direction. But there are many different types of loads. These loads sometimes may even be, for example, the organelles. So these motors are able to pull the organelles around inside the cell. So depending on what it is, it will attach to that and then to the rail and work. But see, all these are actually mostly random processes. So it may start that way, it may be able to carry it all the way to the destination, or it will get detached, but again randomly it will attach to another rail, microtubule rail, and continue its movement. With all these detach-attach operations, it may fall back. See, you have taken some distance, and you get detached from a random movement, and you may attach to another rail, or maybe the same rail, in a position which is you have lost some distance, or you may be lucky, and by just floating, you may just fall to a position. Once the motors, sorry, we already discussed this. With regard to the routing along a microtubule track, several possibilities occur when a motor reaches an intersection of microtubules. The motor can pass the intersection along the same microtubule. So we're talking about intersection points. You start from this rail, and you have a cross here. You may go over the same microtubule. That's one possibility, which means actually ignoring the intersection, just continuing. the motor can pause at the intersection. It may just stop there. The motor can switch to the perpendicular microtubule, which means take a left or right turn in the microtubule. Or the motor can simply disassociate at this intersection and again start floating with Brownian motion, and God knows what will happen. Okay? Any one of these may happen. But it has been observed that in most of the cases, the first one occurs. You go straight, or you get disassociated from the rail. Turns are less likely. Some work also has been done on steering such small structures, making them move in the way you wish. In the experiments, kinetic motors are attached to a surface, and a microtubule filament is transported by the operation of the stationary molecular motors. Now, what does that mean? This means the following. Now, what we have discussed up to now was you have the rail, you have the heads attaching and walking on this rail with the neck attached to the load, right? This is another layout. In this case, there are many motors. They're attached to a surface the other way around. They're fixed from the neck. And the legs are just free. And then you take a microtubule filament and put it over this layer of molecular motors, and you're able to direct the, and see, when you put this, now this time the filament comes over the heads. So the heads connect to the filament, but when they do this attach-detach operation with the ATP hydrolysis, since they're fixed, they're actually moving the filament. Okay? This is like what happens in rock concerts. Okay? This is called crowd surfing. Okay? This time you have the molecular motors fixed. With the movement of the heads, actually you're pushing the filament in the reverse direction. And it is possible to control the direction of the operation. Okay? This is being done. Since the kinetic motors in this case are stationary, it is the microtubule filament that is actually moving. And by applying an electric field, the section of microtubule being transported can change course by up to 90 degrees. So you can make it take a right or left turn, running parallel to the electric field towards the positive electrode. And the microtubule segments have been actively steered using this mechanism into the desired channel of a Y junction. You have a Y junction. You can decide whether the filament will take a left or right turn at that Y junction. How a transmitter emits the information and how the receiver picks it up is an important question. One approach is to use a form of ligand-receptor binding. A ligand is a substance that's able to bind to a biomolecule, and it forms a complex that can serve a biological purpose. So you can put the ligands, for example, at the cell membrane to attract and attach to the incoming molecules, messenger molecules, for example. It can be a signal triggering molecule binding to a site on a target protein by intermolecular forces such as ionic bonds, hydrogen bonds, and van der Waals forces. The binding is usually reversible, so they can attach and then detach, which is ideal for cargo loading and unloading from a molecular motor. Ligand binding to receptors alters the chemical conformation. That is the three-dimensional shape of the receptor protein. And the conformational state of a receptor protein now determines the functional state of a receptor. So the tendency or strength of binding is called affinity. At the moment we are discussing what's going on inside the cell with the molecular motors, but we'll see that affinity becomes important also in the case of intercellular communications. Like you have ligands, as I mentioned, on the surface of the cell membrane, and if the molecule gets close enough to that receptor, the receptor is able to pull the molecule towards itself, okay? So that they don't have to just be exactly aligned in 3D. Once it's close enough, the receptor can pull it in a way that this coincidence will be likely. So one particular form of this approach is mentioned in 19 and 20 by specifically using an avidin-biotin binding to load information molecules onto carrier molecules, partly answering your question. It should also be noted that the tail of the molecular motor has a very complex structure, allowing it to bind to many different types of cargo, but still specific types of cargo. So each molecular motor is able to carry selected types of molecules, and different parts of the motor can bind to different surfaces. Let me stop at the topic of hybridization and leave this to the next week. We'll be stopping here for today, and next week we'll start from this position. If you have any questions before we stop? Okay, none? Okay, see you all then next week.